Hey all, Rusty Rob here. Welcome to another video. This time we'll try solve one of my favorite problems from codejam. So this is way back from codejam 2013, and I think it might have been one of the first codejams I did. And so I solved a couple of the basic problems, but this one was just out of reach to me. And I remember seeing the solution and thinking, wow, that's really cool that someone could come up with that problem. It's just really elegant. And so let's solve it today. I mean, been, it must have been about 10 years ago actually, but I can still kind of remember the problem. So hopefully I can solve it, or at least write some code that almost solves it. So yeah, let's go into it. I'll kind of just read the problem, then I'll draw a few diagrams showing the layout of the problem and some approaches, and just kind of think about the approach, and then I'll code it up in Rust. Let's get this video out the way. Okay, so treasure. So you're following an old map and you stumble upon the Dread Pirate Larry's secret treasure trove. The treasure trove consists of n locked chests, each of which can only be opened by a key of a specific type. So already it's pretty exciting. As a kid, I always thought pirates and treasure chests and stuff were pretty cool. Imagine being at the beach and finding an old treasure chest. That'd be pretty cool. Furthermore, once a key is used to open a chest, it can never be used again. Inside every chest, you will of course find lots of treasure. You might also find one or more keys that you can use to open other chests. A chest may contain multiple keys of the same type, and you may hold any number of keys. You already have at least one key in your map says what other keys can be found inside various chests. With all this information, can you figure out how to unlock all the chests? Okay, and then they've got this example. And they say you could open them in the order 2, 1, 4, 3. So I'll draw this example up. It's a pretty good example. And next color draw. What else does it say? For each case, output one line containing chest 1, 2, and n, where x is the case number and where CI represents the index starting from 1 of the ith chest that you should open. And then here it says if there are multiple ways of opening the chest, choose the lexigraphically smallest way. So that kind of implies you should greedily kind of choose the lowest chest first if you can. Maybe that's a hint that there's a greedy algorithm for this. We'll have a look into it. But it also means we have to be quite careful. Alright, so here they have chests numbered 1, 2, 3, and 4. And the first two have a key of type 1. We can imagine that as like a blue key or something. And then there's key types 2 and 3. So I'll draw those. So 4 chests. 1, 2, 3, and 4. And 1, and 1, and 2, and 3. And then these chests will contain some keys. So the second chest has keys 1 and 3. And the last chest had key 2 in it. Alright. And then we also start off with some keys. You began with exactly one key of type 1. So we've got key 1. So already you can kind of see a bit of a graph. And then from here we can get keys 1 and 3, which means we could go like this. Or we could go like this. And from chest 3, we can go like this to chest 2. And we have to open all the chests, even the empty chests, because they got treasure. So if we wasted the first key on chest 1, then we could no longer open this chest, and then we could no longer open these chests, so that wouldn't be good. Just starting to get a bit of an idea for an algorithm. We also want the lexically lowest order, so it kind of feels like we should try, first we should try like this one, and then we should try this one, and so on. The problem is, like, what if we were opening chests successfully, and then we got all the way to the last one, and then couldn't open it. Then we went back and tried swapping the order of these two, and then we get to the last one again, and it doesn't work. So then we go back further and swap, and so on. It looks like there'd be like n factorial different ways, which isn't good. We'll just check what the limits are. So there's only 200. N is the number of chests, I think. Number of keys and the number of chests. Okay. And there will be at most 400 keys altogether. Okay. Says all key types will be integers between 1 and 200. Okay. And I remember these limits are deceptively small, so it's like, oh, I need a complicated algorithm that can do lots of compute. But it turns out there's an n squared solution, I think. So they could have made these limits higher, so they kind of throw you off. All right. So yeah, I said before it kind of implies there could be some greedy kind of element to this. So like we kind of have to go through these chests left to right and kind of at each point kind of know like can we take this chest or not. So for example, if we took this chest, we know that we can no longer open this chest, so it's not good. So we know all of the lock types. So we need to make sure after opening this chest that we can still access all the available lock types. And for us to like greedily take this chest before this chest there, if we open this chest and we know it's still possible to open this chest, then we kind of kept our options open, so it doesn't really matter. We can just greedily take this and it's lexicographically lost, so that's better. Whereas let's say we opened this chest and now it's no longer possible to open this chest. Well, then we know that we shouldn't have opened this chest. So how can we know which chest is still possible to open after opening this chest? Well, let's just say we have some keys here, and then we have some chests, and then we have some key types, which then we can kind of make a bit of a graph. So from the keys I have, I can access various chests, and from each chest I can access various key types, right? And so at each step, I guess from the chests that are still not opened, we know the various locks that these chests have. So it makes sense we need to be able to get a key of each. If we look at so from the keys that we have, we can traverse this graph and get all of the reachable keys. So for example, from this key, I could go to this chest and then I could get this key, and then maybe that key helps me open this chest over here, which helps me open this chest over here. So it's just a breadth first search, a depth first search. So that would be reachable keys. So we can calculate reachable keys. And we have the keys that we have. And actually we could, this graph we could actually just make more direct like this, I suppose. But I guess it doesn't matter too much either way. So how do we, I'll increase this font size a bit. So how do we decide if we can open a chest? I think it'll be like the keys we have plus the keys we gain from opening the current chest minus the lock of the current chest plus the keys reachable from, let's just say, gives us a set of key types. From the set of key types, we can do a search. So step first search what all the types of keys we can reach. And then for all remaining unopened chests, this gives us a set of locks. Are all of these locks included in the set of reachable keys plus the set of, what was this other set of keys? It gives us a set of key types plus the set of currently available keys. Yeah, so I think some logic kind of like that. So let's think about data structures. We'll probably have like a variable called my keys, which will be a hash map of usize to usize, which is just for each key type a count of how many there is of that type. Then there'll be chest, which will be a vector of chest. And so we have a struct chest, and that's going to have the lock, which will be a usize. We'll have keys, which the keys that are inside the chest. So that'll be hash map of usize to usize. And then we want to know, is it opened? That's a Boolean. And then the order, which is like a usize, because at the end we've got to print out, we got to print out the ID of each chest. So yes, we can use that order later to print the result. I guess this should be option usize, because it won't have an order until we find that we can actually open that chest, and it could be impossible. So in that case, we print impossible. Now, if the order is none, then we know it's not opened. So we don't really need this. But I'll just keep this for readability, I guess. Not too worried about performance. Yeah. So I guess we'll start coding. So copy this sample input. And what is it? So we got the first number is the number of test cases, then you got number of keys and number of chests. Then you get all of the keys that you start with, and then you get all the chests. So here you start off with just key number 1, and then I guess this is the first chest, which is of lock type 1, second chest, lock type 1, containing these keys, and so on. Oh, no, 2 is like how many keys are inside, so it contains keys 1 and 3. So here we have 1 and 3. Okay, yeah. So, cool. Give this a try. So we need a get line method that returns a string. So we need a buffer. I mean, sometimes I have some input-output code ready. I haven't done any Rust for a while, so it's nice getting back into some Rust. Standard dot, what is it? How do I read input? Thank goodness for autocomplete. And then we should trim. I think we need to trim. I don't know. I always remember that trim returns a reference to the string reference or whatever you call it. So this will just convert it into a string. And okay. So now we can get a usize to get the number of test cases. So we'll go get line dot parse, and we'll parse that into usize. We could make this generic if we wanted to, but we're only using usizes. Okay. And then we need to get usizes as well. So that will be a vector of usize. And we'll just get a line. So then dot split. v.push part.parse usize. And once again, this could have been generic as well if we'd wanted. Okay. So t will get usize. Okay, we need our chests, so I guess we'll go read our keys first. So let my keys equal hash map. We'll just read the keys, I guess. So for key and let's call it K. For K and oh wait, it wasn't each test case had. Oh, we need to look through all the test cases. So for case num and 1 dot dot equals t. I guess I'll just read it all in here. I could make a solve method, but I don't think we need that. So for k, and we need to read how many keys there are, right? What was it? It was number of keys and number of chess. Okay, and then okay. So can you go like this in there? So I forgot. Don't think so. I think it was K first, right? No, wrong spot. Um, what am I doing? I don't even need to do this because they're all on one line. Okay. So here we're counting how many of each key we have. What's wrong with this? Okay. Sorry about that. Just a little bit rusty with Rust. Looking forward to getting into it a bit more. Keen to get a few video ideas like Snake AI, Rubik's Cube, that can solve itself. A few other things, robotic arm and stuff like that. Okay, so we've got all the keys. Now we want some chess. Make a struct. So what did we say it had? It had the lock. It had the keys. It had the, if it was opened. Maybe we'll call this is opened. And then it had its order. And that'll be option. Okay. Is open maybe? Ah, oops, no. I'm doing too much TypeScript. Okay. So net n equal problem info 1. to give this a tap. And then I think Chess needs to implement clone for this to work. Oh, no, that's just the capacity of it. That's cool. Why not just go like this? We'll drive default. Oh no, we'll just stick with this. Maybe we could make a read method on chess itself. Okay, so nums will be get users, and the first number was the lock tab. So num0, we'll just do this. Then the keys will make a hash map. Maybe I'll just copy this one. Okay, let's have a look. So remember it was 1 and 3, right? So 2 is how many there are. Okay, guess we can just go for key and nums2 onwards. Five cannot be known at compilation time. Let's go. Not sure what that is. Skip. We'll skip 2. Dereference that. So entry k default plus equals 1, and you have to do that. Okay. Nice. That should work. Yes. So push. This needs to be mutable. Okay. May as well just print this out. Oh, is that right? Okay. Let's print this out. that. Alrighty. So for that first case, the first check has lock 1 with no keys. Second check has lock 1 with 1 key of type 3 and 1 key of type 1. And the last chest has lock 3 with 1 key of type 2. So that looks pretty good. And just to double check, here's our diagram. So 1 and 3 and 2. So it's looking good. Alright. Now for the hard part, we're going to solve this, huh? So let's just say we solve. What do we need? Should my keys be mutable? We need my keys and we need chess to solve it. I'm not quite sure how that works yet. And then what do they want? The order of the chess, the ID of the chest. So chest number 2, starting from 1 instead of from 0. So for if chest order is none, or we could just go if it's not open, possible equals false. Okay, so what do we want? We go through an order. So for odd, and we'll just do zero-based ordering. So if the chest the order is equal to the order, of course. It's mutable. And we need to add 1. Make this a string. got that out the way. That's just, yeah. I mean, it would have been nicer if we just collected the test IDs as we went along. But, oh, now the solve method should be a little bit more simple. This needs to be mutable so we can add the orders in and stuff like that. Do we need the solve method? Guess not. Let's just say while let mu I equals 0, while I is less than n, if chess I, if it's not open, then let's try to open it, and can open. Not too sure what that's going to be yet. If it is open and we can open it, then then we need to add keys from chest, remove destroyed key, and increment I. So we'll go I plus equals 1. No. If we open it, we want to go back to 0 because we always want the lexicographically lowest. So we just go back and we just keep scanning through until we find one. Each time we find one, we stop. Otherwise, we just go to the next chest. Hope this should work. So for key, count in chest I dot keys, my keys dot get, okay, or default entry, entry or default. Okay. Then we also need to go my keys. We also need to make sure we actually have this key. So my keys dot get just I dot lock is greater than some. The only thing is, I think none is negative infinity, or is it plus infinity? Maybe I won't do that. Unwrap or 0, greater than 0. Expected at ESRs. Really? Let's rename this for simplicity. Has key equal that. Don't know. So we also need to remove that key that got destroyed. Okay. Okay, so I think this looks good. So I think all we need to do is this. Is that right? Hope so. So we'll know. Can we open chest I? And we'll give a reference to the chest. Yeah. So I think we will make a helper function for that. Mutable reference to vector of chest. And we'll return a boolean. What's he complaining about now? Can't move. What if we go like this? And just realized this should be count. Okay. So now what do we need to do? We kind of described it a bit here. So we need the keys that we have. I didn't like this being a mutable reference actually. Seems complicated. Can it just be a copy? So then we just mutate chess and my keys here. Oh, so I need to set this chest as opened as well. So let's go chest I dot is open equals true, and chest I dot order equals some order. What should that be? Another variable order. Oh, let's call this. I think we wanted that zero best. Okay. So now what? You need to build a graph. So the keys we have will be for key of chess I dot keys. Keys. Don't like all those red underlines. So just put true down there. And this isn't TypeScript and not of. Shouldn't this be star as well? Okay. So I've got some keys. And we want to see all the keys that we can reach from here. So it let's build a map of keys to keys. Just trying to think. Should I just make these lines direct? So this was the keys we have. And this is the chest, and then this is the keys at the types of keys. These are the types of keys we have. This is the chest, and then this is the types of keys that those reach. Probably doesn't matter too much either way. Then I have to go to each chest and then to the keys. But essentially we just want the reachable keys. So from this key I can go to this chest, and then I can go to here, and then I can go to here. But I just have to remember, okay, I've visited this one. Like I don't want to go back to that one again, and I don't want to go back to that one again. So I need 2 visited sets. Yeah, I guess I could just do 2 visited sets. Visited keys and visited chest. I mean, it would be faster if we built this all up front, but I don't think it's going to matter too much. The limits are pretty small. Actually, you're going to have to iterate through all the chests to see, because I don't have a map looking to the lock of each chest. So when I'm trying a particular, I can't just go direct from a key to the chests of that type. So let's just build a graph from keys. So key to keys. So it's like from this key, which keys can I get? So it'll just be a hash map. The key type, and then it's to a hash set of all the keys that it can reach. All right. So I guess I couldn't have built this graph up front because it changes because it depends which chests have been opened so far. And I guess I could have deleted chests from this array, but I wanted to keep them so that this code back here works. Then I would have had to store the index of each chest, but I don't want to do that. So let's build this graph. Maybe I'll just call it graph. So for chest and chest, what's wrong? It's already a reference. Entry if chest is open, then just continue. insert, what do you want to insert? All the keys. So for key, type in keys.keys. Yes, that's just the keys of that hash map. I wonder if there's a shorthand for this. I'll try to do this in one line. Dot extend chest dot keys. Cool. Okay, so now we've got a graph, I think. We want to work out all the keys that we can reach. So let's do that first search. So we need a stack. I don't know why I counted these. I only need to know the types of the keys that I have. I also just realized a bug we have. So it's not just enough to know, can I reach each type of key? I need to have enough of each type of key as well. So I'll just pause here and go back and check we have enough of each type of key. Let's just say total block count. we want to count how many of each type of key we have, and then we need to count the locks and just make sure we have enough of everything. So we go for K, and for lock, comma, count, total lock count, this code's actually getting pretty messy. This is why I should have made like a helper function that could return false if it's not possible. And then you can always return early. Maybe I should do that. So we'll solve maybe same as this. Should I just go case num? We'll just say return string. Okay. Yeah, that was a bit of a tangent. What's wrong with this? No, it's a string. Okay, so now we need to do that first search to see what's reachable. Don't think I need these counts. I just need the starting key tips. No, I guess. Then we also have a bug here. We should skip just I. It shouldn't be part of the graph. And so this could become 0. So we just don't want to add it to the stack if it's 0. So for k and keys. Okay. And they're not visited yet. I guess we can regard it as visited. Did I already make a thing called visited? No. That visited. Okay. So now it's just your standard depth first search. Oh, the stack is now empty. Let's k equals stack dot pop. Actually, sorry, this is nicer. Okay, goes. We'll let some k equals stack dot pop. Return true. This way has been I've never used this unwrap or default thing. Default is not satisfied. This is better. Greatest child if not visited contains child. Then we'll edit. And add it to the stack so that we can search that child later. Let's just say, so now we've searched all the types, but we need to record what's reachable, right? And what did we want to do with all the reachable items? Make sure every chest is reachable. Okay. Well, visited will contain everything. So now we just need to go for chest and chest, not counting I. Copy this thing again. If not visit that contains that lock. So we have that lock and we never visited a key of that type, then it's not possible. Okay. Cool, so I think we're done. Seems strange we're not using the case number anywhere. guess we don't actually need the case number because I do the printing elsewhere. Solve test case. Alrighty, moment of truth. Impossible. That's not good. For some reason, I just had a feeling it was going to work. Probably there's lots of bugs then. So I guess we can log what's happening here. Oops. So going through each chest. Did we ever get here? Oh, we did. I'll skip other cases. So return. We'll just debug the first case that we know about. No. I'm sorry if there's a lot of background noise. I don't know if you can hear that. It sounds like baby's having a lot of fun out there. Okay. So that seems good. Oh, I guess I need to backtrack. I don't know why I used the while loop then. Should have used recursion. I don't know. We greatly knew we could take that. And then we kept our options available. So if we should have taken another chest instead, it wouldn't have. That's not possible because we can still take that chest later on, even when we take this chest. So that's fine. Let's see what we visited. So with chest 0, we then couldn't reach anything. If we went to chest 1, then we could reach chest 3, 2, and 1, which seems good. So I guess then we take that, and then we're back at chest 0 again, and we have keys 2 and 1 from keys 1 and 3. Keys 1 and 3, but then we used key 1 to open this one. So we can reach 3 and 2, which makes sense. What is the solution? It should be 2, 1, yeah, and then 4, 3. That's right. When we get to number 3, then we can go 2, 1. How come there's no 2 here then? Because when we get to 2, we don't actually have that key. I'll print the keys that we have just to double check. So I'll just go print I, and we'll print the keys we have. I keys. So we start off with key 1. We didn't go for that one, so we still got key 1. We go for that, so we grabbed a key 1 out of that, and then we grabbed a 1 and a 3. So now we just have keys 1 and 3. So yep, 1 and 3. Now we are at 0, and that's fine to go for 0. So now we lost our 1. Now we're at 1 again, and it doesn't matter. We just, because chest 1 is open, so we're going to skip that. So now we're at 2. So we have a 3 and a 1, and we don't go into chest 2 because we don't have the key for it. I'll just double check that, but has key. So we don't even have the key yet. So we have to go to 3 first. So, oh, just print. I'll just check, do we actually open chest 3? We opened 1. We should have opened 0. Why didn't we open 0? That's a bit weird. So we didn't even open 0. Can open. Okay, so we can't open 0. We go to 1, and yes, we can open 1. Go back to 0. Why couldn't we open 0? As you can see, the visited values at 0 are 3 and 2. Oh, So we need to remember if the chest is already open, then we don't need to open it either, right? Okay. Still says impossible. So what's going on? So yes, we can open 1, then we get to 0. Let's just print this out then. So we open 1, then we're at 0, and nope, 1. But chest 1, this should already be open. We already opened chest 1. So why is chest 1 not open? Where? That's the lock. What was the lock? What was I? I2. Oh, this should be I2. This should be I2. Oh, this should be I2. Maybe that was the bug. There we go. 2143. 2143. So get rid of all these logs. Get rid of the return statement. Please work. 1, 2, 3. And impossible. Alrighty, let's try to submit. Rust. I'll just submit. Come on. I don't know, 50-50. Compile error. They've got an old version of Rust. That's annoying. Let's run it in test mode. Runtime error. Because I had the wrong input. So I guess that shows that there's no compile error, but I'll just run the test anyway. So now I'll turn off test mode and get ready to submit. Submit. Come on. Come on, baby. Yeah. So pretty stoked with that. How long have we been recording for? An hour and a half. Oh, that took a while. Yes, I'm a bit out of practice with this kind of stuff, but super fun problem. So if you haven't tried that one, I definitely recommend giving it a try. And maybe see some of you tomorrow, since they're running a few problems for the last ever code jam tomorrow. So yeah, enjoy that if you do it, and subscribe because I got a few cool videos coming up. I created a pretty awesome Wordle solver. Um, there's a couple of code jam problems where I found uh, more optimal solutions than in the editorials. So some cool kind of tricky little algorithms for that, and one for Hacker Cup as well, where I found a faster solution than what they have in the editorial. And then yeah, we'll see if I have time. Maybe robotic arm with do a bit of 3D graphics, Rubik's Cube, um, and some other things like that. Anyway, thanks for watching and see you later.